Hello and welcome to MeduHub. I am Neha Gupta from the chemistry faculty, and today's topic is going to be phenols. Phenols are a class of organic compounds where an OH group, that is a hydroxy group, is attached to an aromatic hydrocarbon. So the simplest of phenols would be, we'll have a benzene ring to which an OH group is attached. So this hydroxybenzene is also called phenol. Phenol is the accepted IUPAC name and the common name for this hydroxybenzene. This is also called carbolic acid. If we talk about the structure of phenols, in phenol, this carbon here is sp2 hybridized, and this oxygen with two lone pairs is sp3 hybridized. So, this bond length here, the carbon oxygen bond length, is less than what it is in alcohols, because in alcohols the oxygen is attached to the carbon which is sp3 hybridized, and here the carbon is sp2 hybridized. sp2 hybridized carbon is more electronegative, it has more s character, so it pulls the electron from this bond more towards itself, and hence this bond length is shorter, 136 picometer. Also, the lone pair on this oxygen is involved in resonance with the benzene ring, like this. Because of this, this carbon-oxygen bond gets a partial double bond character, because of which this bond length shortens further. So this bond length is less than that of an alcohol's CO bond length because of two reasons. One is the sp2 hybridized nature of the carbon, and second is the plus R effect or the resonance effect, where this lone pair is in conjugation with the benzene ring, giving a double bond character to this bond, right? If we talk about classification of phenols, they can be classified into three categories. First is a monohydric phenol. Monohydric phenols are when only one OH group is attached to the benzene ring. So, simple phenol, or this one here, OH, and let's say CH3 attached here, is a monohydric phenol. The second class category is a dihydric phenol. Dihydric phenols are when two OH groups are attached to the benzene ring. So, for example, one is here and the other one is here. When two hydroxy groups are attached, it's a dihydric phenol. And the third category is called a trihydric phenol. In trihydric phenol, as the name suggests, three hydroxyl groups are there. For example, this is the benzene nucleus and three OH groups are attached. So this is a trihydric phenol. So let us see how phenols can be named. What is the nomenclature? So if we talk about monohydric phenols, these three examples here are examples of cresols. Cresols are phenols in which a methyl group is attached. So when the methyl group CH3 is ortho to the OH group, it is called orthocresol. Orthocresol is the common name of this cresol. Now, if you talk about the IUPAC name, with respect to this group, this is the second carbon. Alright, so this will be 2-methyl phenol. Alright, coming to this, here the methyl group is at the meta position with respect to OH group. So this will be metacresol. And if you talk about the IUPAC name, this is 1, carbon 2, carbon 3. So this will be 3-methyl phenol. And here, the third one, here the methyl group is at the para position with respect to this OH group here. So this is called para-cresol, or the IUPAC name would be, this is the fourth carbon with respect to this carbon here. So 4-methyl phenol. Right? Now, if we talk about dihydric phenols. Dihydric phenols are when there are two OH groups present. So the first example here is when the two OH are ortho to each other. When they are at ortho positions, the common name is catechol. And the IUPAC name would be, this is carbon 1, this is carbon 2. It will start with benzene. Benzene 1, 2 diol. Right? So you will not say phenol. This is a benzene molecule, benzene nucleus, which has two hydroxyl groups. So that is diol. The position is 1, 2. Here, in the second example, this is called resorcinol. Resorcinol is the common name when the two OH groups are meta to each other. So this is carbon 1, 2 and 3. So how will you name it? This will be benzene 1, 3 diol. Alright. In the third example, the OH groups are at para positions, carbon 1 and carbon 4. The common name is hydroquinone or quinol. The IUPAC name would be benzene 1, 4 diol. So this is how you name dihydric phenols. You start with benzene and then tell the exact positions of the two OH groups, and you have a diol here because there are two alcohol groups present. Next, if we talk about trihydric phenols, the first example here is where these two, this is carbon 1, this is carbon 2, and the third OH is at the fourth position. Why will we start the numbering from here and not there? Because of the lowest locant rule. Alright, this is 1, 2 and 4. The common name is hydroxyquinol. What will be the IUPAC name? It will be benzene 1, 2, 4 triol. Or there's another way to write it. 1, 2, 4 trihydroxy benzene. Alright. Coming to this example, this is pyrogalol. Here, the OH groups are at carbon 1, 2 and 3. So, 3 OH groups present. The IUPAC name would be benzene 1, 2, 3 triol, or we can also write 1, 2, 3 trihydroxy benzene. In the third example here, this is fluoroglucinol. Here, this is a symmetric trihydric phenol molecule. Here, OH is at carbon 1, 3 and 1, 2, 3, 4, 5. This can be named according to the IUPAC system as benzene hyphen 1, 3, 5 triol, or 1, 3, 5 trihydroxy benzene. So this is it about the nomenclature. Next, we need to see what are the physical properties. There are two physical properties that we will be discussing. One is the boiling point. So basically, the boiling point of phenols varies on the size of the aryl group and the number of carbon atoms in the molecule. So if the number of carbon atoms in the molecule increases, the magnitude of van der Waals forces increases, and hence the boiling point increases, right? And if you compare phenols to molecules like aryl halides or aryl ethers of comparable molecular mass, then you will realize that phenols will always have a higher boiling point. Right. Here we have discussed that as the molecular mass increases, with the number of carbon atoms increasing, the boiling point will increase because the van der Waals forces of attraction will increase. But if we have two molecules to compare, one is an aryl halide and other is a phenol, which have comparable molecular masses, phenols will always have a higher boiling point, and that is because of intermolecular hydrogen bonding. We have phenol molecule here and we have one here. So this hydrogen will have intermolecular hydrogen bonding with this oxygen here, and so on and so forth. Because of these forces of attraction, all the molecules will be more attracted to each other, and hence the phenols will have a higher boiling point. Next physical property is solubility. So like alcohols, phenols are also partially soluble in polar solvents, and that is again because of their ability to form hydrogen bonds. So if we have phenol and we talk about water, right? So this hydrogen here will form hydrogen bonds here. We have more water molecule. They will form hydrogen bonds here also, and so on. So because of this, but this aryl group is water repellent. But because of the ability of the OH group to form hydrogen bonds, phenols will be partially soluble in water. And as the size of the aryl group increases, the solubility obviously decreases. Next very important topic is acidity of phenols. So there are two major reactions which show us that phenols are acidic in nature. One is the reaction with metals like sodium or aluminium. So we have phenol which reacts with sodium to give us sodium phenoxide. This is sodium phenoxide and H2. Hydrogen gas is released. This tells us that phenols have an ability to give up this proton here, right? Which makes them acidic in nature. The second reaction is reaction with bases like NaOH. So if phenol is acidic, it will react with the base to form a salt and water. So phenol react with NaOH to give again sodium phenoxide to the salt H2O. These two reactions show us that phenols are acidic in nature. Now we need to understand why phenols are acidic in nature. What is it about their structure and properties that make them, which makes them acidic in nature? That means they are proton donors. What makes this proton easy to be donated from the phenol molecule? So if we compare phenols to alcohols and water, you will see that phenols are stronger acids than alcohols and water. Stronger acids. So the first reason is the nature of the carbon atom, the hybridization of the carbon atom to which the oxygen atom is attached. Here in phenol, the carbon is sp2 hybridized, whereas in alcohols, the carbon is sp3 hybridized, which we have discussed earlier. Okay, so sp2 hybridized carbon is more electronegative. Because it has more S character, and hence it pulls the electron pair between these electron pairs are pulled more towards this carbon, and hence the ease of liberation of this proton is much higher when you compare it to alcohols, where the carbon is sp3 hybridized. The second reason is resonance. If we talk about a phenol molecule, oxygen has lone pair of electrons. They are involved in conjugation with this benzene ring. Okay. And OH group has a plus R effect. So these two will come here. This moves here to give a negative charge, and we can draw the resonating structures. Negative charge comes here, double bond here, a positive charge on oxygen here. These two bonds remain as it is. In the next structure, this negative charge would move here to form a bond. These electrons meet here. We get a double bond here. A negative charge here. This stays as it is. And so on. Here, what do you see? The oxygen atom is acquiring a positive charge. Because of this positive charge, the electrons in this bond here are pulled more strongly towards the oxygen, and hence the ease of liberation of a proton here is increased. So a proton can be lost easily because of the positive charge on oxygen, which is due to the resonance effect of this OH group here, and hence this implies since a proton can be released easily, phenols are more acidic. Understood? The third reason is the stability of the conjugate base. If we talk about an acid, it will ionize, giving us a conjugate base and a proton. If that conjugate base is stable, this means that this reaction would want to proceed in the forward direction, because any reaction will move in a direction where there is more stability. So if for an acid, the conjugate base is more stable, that acid would be a stronger acid, right? So if we talk about ionization of alcohols, if ROH, they will ionize as RO minus plus H plus. This is an alkoxide ion. Right, if we talk about phenols, we have this phenol ionizing as a phenoxide ion plus H plus. This is phenoxide. And if we talk about phenols ionizing in water, this reaction takes place. In water, phenols again ionize to give a phenoxide ion and H3O plus. A proton is released which is taken up by water to give us H3O plus. Alright, so the conjugate base here for alcohols is alkoxide and for phenols is phenoxide. Now, there is special stability associated with the phenoxide ion. How so? Because of resonance. If we draw the resonating structures, this is a phenoxide ion. This negative charge moves here, this moves here. The next structure can be drawn like this, double bond here, negative charge here, this and this. Now this moves here, negative charge goes to this carbon, double bond here, negative here, here, and so on and so forth. So how are we saying that this conjugate base of phenol is more stable than phenol? Phenol is also resonance stabilized. This phenoxide ion is also resonance stabilized. But if you look at phenol, here, there is separation of charges. So there is a positive charge in oxygen here, and this negative charge is getting delocalized over the benzene ring. Whereas in phenoxide, only this negative charge is getting delocalized all over the molecule. So because of that, this is more stable than phenol. Hence, whereas if we talk about alcohols, the alkoxide ion has a localized negative charge on this oxygen. So phenoxide ion is a more stable conjugate base and which makes phenol a more stronger acid. This resonance stability is so important that phenol is 1,000,000 times stronger acid than ethanol. Okay, now what do you think will be the effect of ring substituents? Ring substituents on acidity of phenol. So first, if we have a substituent like a methyl group, for example, in cresols. Okay, a methyl group has a strong plus I effect. So what happens if we'll talk about these with respect to the stability of the phenoxide ion. So if any of the substituents is making the phenoxide ion more stable, that means that particular molecule will be more acidic, right? If the conjugate base is more stable. If it is reducing the stability, that means this substituent is making that molecule less acidic. So here the substituent in cresols is CH3, a methyl group. Let us see if we have the methyl phenoxide ion. This is orthocresol. Similarly, we can talk about meta and paracresol. So here, because of the plus I effect, this methyl group is releasing the electron density in this direction. Also, this negative charge on this oxygen also wants to come into conjugation with the ring. So these two negative charges, both of them want to come inside the ring. And because they are negatively charged, like charges, they will oppose each other. So the presence of a CH3 group opposes the resonance of the minus charge here, the alkoxide ion with the ring, the phenoxide ion with the ring, opposes resonance. Since it opposes resonance, it decreases the stability. Decreases the stability of methyl phenoxide. Since the stability of the conjugate base is reduced, that means cresols are weaker acids than phenol. So all cresols, be it ortho, meta, or para cresols, that is the presence of a methyl group at either ortho, meta, or para position, all of them oppose the resonance of this negative charge, the delocalization of this charge into the ring, and hence all cresols are weaker acids than phenols. Alright, so this was about a substituent which has a plus I effect like a methyl group. What if we have a substituent which is NH2 or OCH3? If we talk about such substituents, because of the lone pairs, of electrons present on nitrogen and 2 present here, these substituents have a plus R effect. And because nitrogen and oxygen are electronegative, they also have a minus I effect. How do such substituents affect the acidity of phenol? So if we talk about, let's say, an orthoisomer here, we have phenol, NH2 here. Now, talking about the stability of the phenoxide ion, let me make it the phenoxide ion. This would want to come into resonance because of the plus R effect. Negative charge is here, NH2 plus, O minus. Now this negative charge will move here. This will move on to this carbon here. So the next structure can be para isomer. Double bond, NH2 plus. This moves here, so double bond comes here. The negative charge is on this carbon here. This carbon. Okay. This carbon has the O minus. Now, the negative charge on this particular carbon here destabilizes the phenoxide ion because it is preventing the plus R effect of this, the delocalization of this negative charge into the ring. Hence, if we talk about a para isomer, the phenoxide ion of a para isomer where the NH2 group is here decreases the acidity because it decreases the stability of the phenoxide ion. So it is a weaker acid than phenol. Okay. Similarly, if you talk about an orthoisomer, phenoxide ion, NH2 here, this will move here, this would want to move here, and eventually when you draw the resonance structures, you will realize that the negative charge is again coming at this particular carbon. That means it is destabilizing the phenoxide ion, and hence both ortho and para isomers are weaker acids than phenol. So when a group like NH2 or OCH3 is attached, which has a plus or minus I effect, at the ortho and para position, the plus R effect makes the phenoxide ion unstable and hence they are weaker acids. What happens when they are at the meta position? I believe there is some noise in the background. Please, I would request you to ignore it. Here, it will move like this. The next structure can be drawn with the negative charge here, double bond here, NH2, and this one here. This negative charge moves here, this moves here. So you will realize that because of resonance with the NH2 group at the meta position, this one is remaining unaffected. But we need to see that NH2 also has a minus I effect, which pulls away electron density towards itself, which means it is helping the phenoxide ion getting stable. So this one at the meta position, the meta isomer will be a stronger acid than phenol because of its minus I effect. So ortho and para isomers are weaker acids because of the plus R effect, whereas the meta isomer is a stronger acid than phenol because of its minus I effect. Now, can you think of another group which has a plus R and a minus I effect? These are haloarenes. So if we have halogenophenols, halogenophenols would be a phenol with a halogen atom anywhere at the ortho, meta or para. Halogens have a plus R effect due to the lone pair of electrons on the halogen atom. Also, they're electronegative, so they have a minus I effect, just like the two examples we discussed earlier. But it has been found that all isomers of halogenophenols are stronger acids than phenol. What does this imply? That irrespective of their position at the ortho, meta or para carbon, they are stronger acids than phenol. This means that their minus I effect is more prevalent because it pulls away electron towards them itself, and because of which the phenoxide ion can come into resonance with the ring, hence increasing its stability. This implies that for all halogenophenols, the plus R effect is less than the minus I effect. That means the minus I effect predominates. All right. Third, we can talk about the effect of electron withdrawing groups like NO2. So if we have an ortho isomer, here's the phenoxide ion, we have NO2 here. Now NO2 has a strong electron withdrawing effect. Okay, so this moves here, this moves here. The next structure will be drawn like this. Phenoxide ion here. Now, this will move here. We get a positive charge here. O minus. Nitrogen is getting a positive charge. Now this will move here. And similarly, if we talk about the para isomer, this is the phenoxide ion. We have like this. This moves here, this moves here, this moves here. So what do you see? You see in that both these cases, in the ortho and para isomers, this group is pulling away the electron density towards itself. which means that the phenoxide ion here is getting stabilized. That is, it is coming into resonance with the ring, and this group is enhancing that effect because it is helping in getting all the electrons towards itself here as well as here. Do you see? And from this carbon also, all the electron density is pulled towards this nitro group here. So because of these, because of the minus R effect of these electron withdrawing groups like NO2, you will see that the phenoxide ion is getting stabilized. So both the ortho and para isomers are stronger at this than here. If we talk about the meta isomer here, this is pulling away electrons towards itself, this moves here, and so on. So there is no direct effect on this carbon. But since it is an electron withdrawing group and it is highly electronegative, this will also pull away electrons. But these two have a stronger stabilizing effect compared to the meta isomer. So meta isomer is also stronger than phenol, but it is not as strong as ortho and para isomers. So an electron withdrawing group like NO2 makes a substituent like NO2 makes the substituted phenol, a more stronger acid than a normal phenol molecule. So this is it about acidity of phenols. Now let us talk about the methods of preparation. Methods of preparation. So the first one is something that you have already studied in haloarenes. In this, we start with a haloarene like chlorobenzene, and this chlorine is replaced by an OH group. So this is an example of a nucleophilic substitution reaction. So how does this happen? We fuse chlorobenzene with aqueous NaOH. So in the first step, chlorobenzene forms sodium phenoxide. And then the temperature and pressure required, you need to note this, 623 Kelvin and 300 atmosphere. High temperature and high pressure required. First we get the sodium phenoxide, which on acidification gives us the phenol molecule. So this nucleophilic substitution reaction becomes easier if there's an NO2, that is an electron withdrawing group at the ortho or para position. This is something that we have again discussed earlier in haloarenes. So I'm just doing the examples again. So if we talk about para-nitrochlorobenzene, the chlorobenzene para-nitro, the electron withdrawing group is at the para position. If it reacts with NaOH and upon acidification, the conditions required are much milder. So we only require a temperature of 443 Kelvin to give us the final product. OH, NO2. How will you name this? This will be 4-nitrophenol. Another example, if you take 1-chloro-2,4-dinitrobenzene, so this would be in this one, Then NO2 groups are at ortho as well as the para position. Here you only require the conditions again become much milder because these two groups at the ortho and para positions make the substitution much easier. Only 368 Kelvin temperature is required. First we use NaOH, second we do acidification, and we will get the product. NO2, NO2. To name it, will be 2,4 dinitrophenol. What happens if all the ortho and para positions are occupied with an electron withdrawing group? See here, NO2, NO2 and NO2. This merely warming with water, warming with H2O gives us the product, gives us the substituted phenol. This will be 2,4,6 trinitrophenol. So this is the first method of preparation where from a haloarene we prepare a phenol. We use NaOH and then it is followed by acidification. The second is from benzene sulfonic acid. So how do you prepare sulfonic acid from benzene? We have benzene with oleum, that is fuming sulfuric acid. We get benzene sulfonic acid, HO3H. This is an example of electrophilic substitution in benzene. Alright. Now from this benzene sulfonic acid, if we treat it with NaOH and we heat it, we will get phenol. The third method is from diazonium salt. To form a diazonium salt, we need to start with an aromatic primary amine. So we have aniline here. It forms a diazonium salt with nitrous acid, which is prepared in situ using Na2NHCl at a temperature of 0 to 5 degrees Celsius. First, we will get benzene diazonium chloride. So this is our diazonium salt. This diazonium salt, when warmed with water, gives us phenol N2, that is nitrogen gas, and HCl. Warming gives us phenol N2 and HCl. So this is how phenol is prepared from a diazonium salt. For that, we need to start with a primary aromatic amine. The fourth method is from cumene. Cumene is isopropyl benzene. Isopropyl group is like this, right? And if you attach a benzene ring to it, we get cumene. So first, cumene in the presence of air gets converted to cumene hydroperoxide, which on treating with a dilute acid gives us phenol and acetone. So in the presence of air, we will get cumene hydroperoxide, OOH. This on treating with dilute acid, which has H2O, we get phenol plus acetal, CH3, This method is used for the mass manufacture of phenol using Q. Alright. Right. So this is it about the methods of preparation. Now we need to move on to the chemical reactions of phenols. The chemical reactions can be broken down into two categories. One which is due to the presence of the OH group. The first two we have already studied in acidity of phenols. One is the reaction with metals like sodium, in which we get sodium phenoxide plus hydrogen gas. And second is the reaction with a base like NaOH, which again gives us sodium phenoxide plus H2O. The third important reaction is esterification. Esterification, which is due to the presence of an OH group. So if we have phenol here, phenol reacts with a carboxylic acid like CH3COH, which is a reversible reaction, to give us an ester OCOCH3 plus H2O. It can also react with acid anhydride. Again, to give us this ester plus CH3COH. This takes place in the presence of CH3COONA, and it can also react with acid chloride CH3COCl, which takes place in the presence of a base like pyridine, to give us the aryl ester plus HCl. Pyridine is used so as to neutralize this, otherwise the ester will give us the alcohol, that is the phenol, back. Okay, so esterification is when phenols react with carboxylic acid, acid chlorides or acid anhydrides to give us phenyl esters. A very important reaction of esterification or acetylation, that is the addition of CH3Cu group, is this one, where we use salicylic acid. Salicylic acid, when reacting with acid anhydride followed by acidification, gives us acetyl salicylic acid. This is acid anhydride. On acidification, this is also called aspirin. Aspirin is of great medicinal value as it is anti-inflammatory, it is antipyretic, that means it has fever reducing qualities, and it is an analgesic also, that means it has pain relieving properties. So a very good example of acetylation or esterification of phenols is this, which is of great medicinal value. Now what is interesting is that these phenyl esters can undergo rearrangements, which are called Fry's rearrangement. So if they are fused with anhydrous AlCl3, aluminium chloride, they can give us a mixture of para-hydroxyketones and ortho-hydroxyketones. Or if the temperature is below 60 degrees, the para isomer predominates. If the temperature is higher, that is greater than 160 degrees, we get the ortho-hydroxyketones. So let's say we have this phenyl ester. On treating with AlCl3 at less than temperature less than 60 degrees, we will get the ortho isomer let me just draw it more clearly. Here, and if the temperature is higher, that is greater than 160 degrees, we will get the para isomer. Or at other intermediate temperatures, we get a mixture of ortho and para isomers. This is called Fry's rearrangement. So these phenyl esters undergo rearrangements and form hydroxyketones. Next are the reactions which are due to the presence of the benzene ring in phenols. Due to the presence of benzene ring. The first very important one is electrophilic substitution. So if you remember from the electrophilic substitution of benzene, we saw that groups with a plus R effect like OH activate the benzene ring towards electrophilic substitution, and also they are ortho and para directing. This means that if a phenol undergoes electrophilic substitution, we will get a mixture of ortho and para products and the ring will be activated. So such substitutions are easier with phenol compared to benzene. The first example we'll take is of nitration. So if we treat phenol with concentrated nitric acid, we'll do concentrated later. Let's do dilute first. With dilute nitric acid at 5 degrees Celsius, since the ring is activated, drastic conditions are not required. We will get a mixture of ortho and para isomers. So this will be orthonitrophenol. Yes. That one will be para-nitrophenol. What happens if we treat phenol with concentrated nitric acid? Because the ring is highly activated and we use concentrated nitric acid, all the ortho and para positions get substituted. So with concentrated nitric acid, phenol with conc HNO3, all the ortho and para positions get substituted and we get this which is called picric acid. Picric acid is a strong acid because electron withdrawing groups are present at all the ortho and para positions. So it's a strong acid. Now the yield of this reaction is very low. So this is of less productive utility, this reaction. Why? Because conc HNO3 is an oxidizing agent. So there are large losses due to oxidation because phenol can get oxidized also. Hence, there is an alternate method which is used where we first do sulfonation. We treat phenol with concentrated sulfuric acid and then we treat it with HNO3 to give us picric acid. The reactions can be written like this. Phenol, when treated with concentrated H2SO4, give us di-substituted sulfonic acid products. This one, when treated with concentrated HNO3, finally gives us picric acid. This is a better method for preparation of picric acid because sulfonic acid substituted derivatives are less prone to oxidation compared to phenol. So when these two positions are occupied by SO3H group, this molecule is less prone to oxidation and those losses due to oxidation products are minimized and we get good yields of picric acid here. Next is halogenation reaction. So if we talk about halogenation of benzene, we need a Lewis acid like AlCl3 or FeCl3 to produce the brominium ion or the chloronium ion, right? Positively charged. But because the ring is highly activated when an OH group is present, there is no need for a Lewis acid. We can directly do the bromination and chlorination. So if we talk about bromination and chlorination, for the second method of halogenation, bromination and chlorination, there are two ways to carry out bromination and chlorination. We get different products, depends on the method that we are using. So if we have phenol and we treat it with, let's say, bromine water, we will get a tri-substituted product. Br, Br, Br. So this will be 2, 4, 6 tribromo phenol. And if we carry out bromination with a solvent like CS2 or CHCl3, we will get a mixture of ortho and para products. So based on the method, different products are obtained. What is the reason? So here you see phenol is reacting with bromine in the presence of water. What happens to phenol with water? Phenol is more acidic in water. So phenol ionizes as phenoxide ion. And a phenoxide ion is more activating compared to phenol. Because of the more activating effect, since the ring is highly activated, all the ortho and para positions get occupied and we get a tri-substituted derivative. Whereas this is just phenol, it does not ionize in the presence of these solvents and hence we get a mixture of ortho and para products. Now what if we want to prepare only ortho-bromophenol? So for that we first protect the ortho and para positions by sulfonation. Let us see how that happens. For ortho-bromophenol, so we start with phenol. We treat it with sulfuric acid. This ortho position and this para position is protected. Now this is treated with Br2 in NaOH. Now The remaining ortho position is bromo substituted now. These two remain like this, forming a sodium salt, SO3Na. This on acidification gives us the desired product, that is orthobromophenol. This is the orthoisomer. Now for iodination, how do you do iodination? For iodination, we first need to prepare a diazonium salt. So we start with para-aminophenol and we get the para derivative para-iodophenol using this method. So we start with para-aminophenol, we prepare a diazonium salt which on treatment with Ki gives us para-iodophenol. So this is para-aminophenol NH2 treated with NaNO2 H2SO4 gives us the diazonium salt. N2 plus HSO4 minus. This now on treatment with Ki, potassium iodide, gives us para-iodophenol. So this is it about halogenation. The next reaction is Kolbe-Schmidt reaction. So in Kolbe-Schmidt reaction, what is happening? In Kolbe-Schmidt reaction, the ortho position in a phenol is getting substituted with a COOH group. All right, what's happening here? First, we convert a phenol to a phenoxide ion. Since a phenoxide ion is more activating, even a weak electrophile like CO2 gets attached, gets substituted in the benzene ring. So we have OH reacting with NaOH, here phenol with NaOH giving us sodium phenoxide. Now this reacts with CO2 to give us this product. This is ortho-hydroxy benzoic acid, or it is also called salicylic acid. Here, this is the reaction. 2-hydroxybenzoic acid or salicylic acid. Now this reaction takes place at 120 to 140 degrees Celsius. And majorly the ortho product dominates. We get COH group at the ortho position. We get a little amount of para isomer also. But if the temperature is greater than 140 degrees, majorly the para isomer will predominate. So this is Kolbe-Schmidt reaction. Next reaction is Riemer-Table reaction. In this reaction, the ortho position gets substituted with an aldehyde group, CHO group here. Okay. The reagents used are NaOH and chloroplast, CH2S3. So we have phenol reacting with aqueous NaOH and CH3L3, we will get is orthohydroxy benzaldehyde. The reaction proceeds via this mechanism here. This is also called salicylaldehyde. What happens? Phenol reacts with chloroform and aqueous NaOH to form this intermediate. Here you can see a sodium phenoxide nucleus, and to the ortho position CHCl2 gets attached. This reacts with NaOH to give us this product where we have again sodium phenoxide and the benzaldehyde groups get attached here. On acidification, this gives us salicylaldehyde. So in a Raymer-Tiemann reaction, ortho position is preferred. But what if the ortho position is occupied? So we take the case of vanillin, where the ortho position is occupied. Vanillin, when undergoes Raymer-Tiemann reactions, we can write NaOH and CHCl3. The benzaldehyde group comes to the para position. So majorly the ortho position is preferred, but if it is occupied, the CHO group goes to the para position. That we can see from this example where vanillin gets converted to guaiacol. Alright, and this is how the reaction proceeds, and upon acidification finally we get this product. Next is reaction with zinc dust. This we have done earlier in aromatic hydrocarbons. So if phenol reacts with zinc, we get benzene and ZnO. The yield of this reaction again is very poor, so it is not used as a method for preparation of benzene, but it is very important to, this reaction can be used to find out different benzene nuclei present in natural products like alkaloids. So using this reaction, you can find out the various nuclei that are present, because this hydroxyl group will get reduced and you will get benzene here. Next is hydrogenation of phenol. Hydrogenation is addition of hydrogen. So if you have phenol, upon addition of hydrogen in the presence of catalysts like nickel, you will get this product. So this is a cyclohexanol. These double bonds are no longer there. Hydrogen is added onto the benzene nucleus and you get cyclohexanol, which is not an aromatic compound. Alright, this is a cyclic compound. Next, last reaction that you have to study is oxidation reaction. So phenol can undergo oxidation. Even in the presence of air, phenol slowly undergoes oxidation and forms brown colored products, which are quinones. Quinones are conjugated ketones. So we'll see if we have phenol, in the presence of chromic acid, which can be prepared using sodium chromate and H2SO4 here, you get benzoquinone. Which are conjugated ketones. So this is it for the reactions. There are two categories. One is due to the presence of OH group, that is reaction with metals, reaction with aqueous NaOH and esterification. Next would be due to the presence of benzene ring. The first important category is electrophilic aromatic substitution, under which we did nitration and halogenation. Next is the Kolbe-Schmidt reaction, where a weak electrophile like CO2 gets added on. The other one was Raymer-Tiemann reaction, where an aldehyde group gets added to the ortho position. Then is the reaction with zinc dust, hydrogenation reaction, that is a reduction reaction, and the last one is oxidation reaction. Alright, to summarize, today we spoke about phenols. Phenols are organic compounds in which the hydrogen in a benzene ring is replaced by an OH group. We spoke about their structure, properties, nomenclature, acidity, why phenols are weakly acidic in nature, their method of preparation, and their chemical reactions. So that is it for today. I'll see you in the next video.